Greetings and welcome to the second unit of the flipped classroom in chemistry. This is Ms. Carr, and today we'll be talking about what you guys have probably wanted to talk about since the beginning of a chemistry class, which is of course our chemical reactions. That's where we get to actually start putting stuff together and seeing what happens. So we're going to start with some of the basics today, and we'll get into the nitty-gritty as this unit continues. And the first thing that we're going to start with is our diatomic elements. Now remember that you do need to remember anytime you see one of these elements as a gas or by itself as an element, it will not exist by itself. It only exists as a diatomic molecule. So if you see hydrogen, oxygen, nitrogen, iodine, bromine, chlorine, and fluorine, all of these guys will exist as a diatomic molecule. So if in reading a formula you read oxygen gas, you should immediately know that that is O2, not just O. So you need to make sure that you have these down in your notes and that you make an effort to memorize them or mark them on your periodic table so that you can remember that these gases exist as diatomic elements. Okay? So once you have these diatomics down, and you might want to pause it so that you can make sure that they are in your notes, we want to introduce how we write reactions in chemistry. Now remember that chemical reactions are occurring around you all the time. Without us even realizing it, chemical reactions are occurring within our body, and they're part of everything that we do. And starting with digestion that occurs after you've eaten a meal. You even have chemical reactions that occur in your mouth before your food even makes it to your stomach. Also photosynthesis. Remember, you have your energy from the sun, and carbon dioxide and water come in, and the chlorophyll catalyzes that chemical reaction, and you end up with oxygen out and the glucose out as well. So the process of photosynthesis is that creating energy using the sun and carbon dioxide and water. That's a chemical reaction as well that you should have talked about during your biology classes. Okay, so a chemical reaction is, just to define a chemical reaction, we want to say that it's when elements join, separate, or rearrange themselves. So you can have two elements that come together to form a compound. You can have two elements that in a compound that separate to form separate elements, or you can have elements that are just shifting around, replacing each other or substituting out one for another. So any of these would be classified as a chemical reaction. An essential skill in chemistry, and this is a skill that you cannot leave chemistry with a passing grade without understanding, is the ability to describe a chemical reaction in the form of a written chemical equation. So this is, I would say, probably the biggest skill that you could leave a chemistry class having had. So this is what chemistry is really all about, folks. So a chemical equation is the description of a chemical reaction by using the formulas of the reactants and the products. Now, some of you guys have probably seen chemical reactions before. Hopefully you've seen them in biology where you were doing the photosynthesis reaction, and perhaps even before then in your physical science classes. So you have reactants. These are the things that react, of course. Again, chemists and other scientists don't tend to be very creative with their naming policies. So reactants are the things that react, and they're always on the left side of the arrow in a chemical equation. Then the arrow is red, produces, or to form. So if you have reactants, react, to produce, and then of course on the right side you have your products. So reactants react to produce products. Your products are always on the right hand side of your arrow. Now you will be asked in upcoming exams whether something is a reactant or a product, and what you need to do is be able to look at the equation and tell, is it on the left, is it on the right, is it reacting, or is it something that is produced? Okay, so we're going to practice writing a skeletal equation. Now, skeletal equations are as you might have guessed from the name, they're the bare bones of what a chemical equation is. Now, we're going to put some meat on those bones a little later, but for now, I just want you to see what a skeletal equation looks like. And the example that we're going to use is the reaction of hydrogen gas, which is, of course, H2 because it's a diatomic, plus oxygen gas, and that's O2 because, again, oxygen is also a diatomic, to produce, and of course, if you could imagine, what does hydrogen put together with oxygen produce? And that's water. So we have hydrogen gas coming together with oxygen gas and producing water. So this type of equation is called a skeleton equation because it only shows those bare bones, right? We're only showing the reactants, and of course on the right we have our products. So we're only showing those reactants, we're only showing the product. We're not showing how much, we're not showing how many, we're just showing this is what we're reacting with this to form this. So when asked to write a skeleton equation, it doesn't need to be balanced, it doesn't need to have coefficients, which we'll talk about a little bit later. It just needs to have the basic elements that you're putting together or taking apart or rearranging. So this is the bare bones of chemical equations and reactions. Okay, it doesn't show the ratios. All right, what we're looking at is just the reactants and the products. So I'm going to give you another example, and that is dicarbon hexahydride reacts with oxygen to form carbon dioxide gas and water. And I bet that if you really think about it, you'd be able to actually write out this formula yourself. Okay, dicarbon, how many carbons would that be? You have di means two, so you have two carbons. Then hexahydride is what element, first of all? Okay, your element there should be hydrogen because it's a hydride. Then you have hexahydride. Hexa as a prefix means 6, so you have 2 carbons and 6 hydrogens, and that reacts with oxygen. And so if we have C2H6 reacting with oxygen, which of course is a diatomic, you have your O2, to form carbon dioxide gas and water. So we have CO2 and H2O. So looking at this skeletal equation, I want you to think, what are your products and what are your reactants? Okay? So remember that your reactants are the things that react. So when you look at this problem, you have dicarbon hexahydride reacting. That means that everything with this dicarbon hexahydride is going to be a reactant. Reacts with oxygen, so this is also reacting, and it forms, which is our arrow, this forms carbon dioxide gas and water. Okay. So again, here you have your reactants, because they're reacting as per the word problem, and the products, which is being produced. That's what's being formed by the reaction. Okay. Always remember, and this is the easiest thing I think to remember, is that reactants react and products are produced. Okay, so the reactants react to produce the products. So reactants on the left, products on the right. Always, always. Okay. There are some additional symbols that we do want to go over with you, and you need to indicate, or you can, it's not always necessary, but you can indicate the state of the matter of a reactant or product by using the following symbols after your formula. So say you are reacting water vapor, it's going to be different than you reacting water that's in liquid form. So we can use the following symbols in parentheses to show that we're dealing with a solid, a liquid, or a gas. So you have S, L, and G, and they'll be in parentheses after your formula. So if you have H2O with an S behind it, that would be solid water, which would be ice, right? Or if you had H2OL, that means that it would be water in a liquid form. Okay? If you had a water vapor, it would be H2O with a G, and that would be water in a gas form. Okay? Now there's one other that you need to be familiar with, and that is an aqueous solution. AQ means aqueous, which means that it is hydrated or it is in water. So if we have, for example, hydrogen chloride or hydrochloric acid, and it's aqueous, that means that it's hydrochloric acid that's been dissolved in water. So that would be an aqueous solution. Okay. So for example, if your word problem says solid zinc reacts with aqueous hydrochloric acid to produce hydrogen gas and aqueous zinc chloride, then your equation would look like this. It would be solid zinc. It is reacting with hydrochloric acid, which is aqueous, reacts to form, okay, and this is the to produce is your arrow, to produce hydrogen gas, that's H2G, okay, because that's in a gas form, with aqueous zinc chloride. So you have zinc chloride here, and it is aqueous. Again, if you're struggling with how to translate this here, this zinc chloride into ZnCl2, you need to come in for tutoring. This is nomenclature going from name to formula. I have some videos on how to do that, but if you're that far behind and you're having trouble struggling there, you need to make sure that you come and see me, because we will run into much larger problems in the next week or so if you're not able to translate this zinc chloride into this formula. So please come and see me if you're still struggling with the nomenclature on this. Okay, I'm going to give you some additional symbols as well. And the first is that sometimes for a reaction we need to add heat or a catalyst. And a catalyst is simply something that makes the reaction happen faster, right? These either are required to make the reaction happen, or they're required to speed up the reaction. So while the reaction might happen without them, it helps make the reaction happen in a time period, in a time frame that we would like. So for example, if I wanted to make a reaction occur that would normally take place over like 3 days, but I only have one class period to do it, often you'll use heat to speed up that reaction. So we would use the symbol delta, which looks like a little triangle, and you would put it directly above the arrow. So for a catalyst, your symbol for whatever the catalyst is, so depending on what catalyst, for biology, for example, we use enzymes as catalysts often, and those catalyst names or symbols will go above the arrow in the equation. So for example, if I have aluminum oxide and I want to break it down into aluminum and oxygen gas, then that is a reaction that requires the addition of heat. So in the chemical reaction, I would put this delta symbol, this triangle symbol, above my arrow. And likewise for a catalyst, for the breakdown of hydrogen peroxide into water and oxygen gas, I would need a catalyst for that, and the catalyst would be magnesium oxide. So I would put my magnesium oxide catalyst on the arrow. That doesn't mean that I'm adding magnesium oxide into this reaction. It's not being reacted, and it's not part of the product. It's simply making this reaction happen faster. Okay? So a catalyst is a substance, and this is one of your vocab words. A catalyst is a substance that speeds up the rate of a chemical reaction, but is not used up in the reaction. It is not classified as either a reactant or a product. Now, our next podcast will look a little bit more into what your chemical reactions are going to look like and what you will be expected to do with them. Okay, you should get started on your first worksheet, which will be identifying some of those chemical reactions.